This is the 16th video in our series on Lie algebras. And in our previous video, we started down a long path of classifying all finite dimensional complex semi-simple Lie algebras. And well, we're working towards understanding something called the root space decomposition as part of that classification. But in order to do that, after our first definitions in the previous video, we need some technical results. And so this video is going to be for those technical results. So I'd like to point out throughout this video, and probably some of the ones in the future as well, or some ones following this video, L will be a finite dimensional complex semi-simple Lie algebra. And then we're going to use the following previous result a few times, so I thought that I would recall it. So each x in L can be written in the form x equals s plus n, where s and n are in L, where the adjoint action of s is diagonalizable, the adjoint action of n is nilpotent, and the bracket of s with n is 0. In other words, s and n commute with each other. Furthermore, if x bracket y is equal to 0, then s bracket y is 0 and n bracket y is 0. So in other words, if a vector commutes with y, then the things that it decomposes into also commute with y. Now I'd like to point out that any linear transformation can be written with a diagonalizable part and a nilpotent part. That's just the abstract Jordan decomposition. The important thing here is that add x, well, is written with a diagonalizable and a nilpotent part, where those parts are also in the Lie algebra. So that's something that is not always guaranteed. That's where this semi-simplicity, well, the fact that we're over a complex semi-simple finite dimensional Lie algebra comes into it. Okay, so anyway, we need one other thing here. And well, this definition will be the subject of most of the video. And it's defining something called a Cartan subalgebra. And so an abelian subalgebra of maximal dimension containing only semi-simple elements is called a Cartan subalgebra. Okay, so our first result will be to show that L contains a non-trivial Cartan subalgebra. Recall, L throughout has these qualities. Okay, so let's get to it. So let's take x in L, and what we'll do is write it using this previous result. So I'll write Sx as s sub x plus s, or plus n sub x, where this add sx is diagonalizable, which is really the same thing as saying s sub x is semi-simple. Remember, an element is semi-simple if its adjoint action is diagonalizable. Okay, so and add nx is nilpotent. Remember, nilpotent is like some sort of abstract version of being strictly upper triangular. So the sum of these makes it upper triangular. Okay, so anyway, so by previous, we know that Sx and Nx are inside of L. And so that's the previous result that we just talked about a bit. So now what we're going to do is argue that s sub x is non-zero. So let's notice that if s sub x is equal to 0 for all x in L, I guess I should say we're not going to show that this s sub x is 0, because here we're taking an arbitrary one. We're going to show that there exists one that is non-zero. And we'll do that by contradiction. So if all of the s sub x's are equal to 0, then what does that mean? That means that x is nilpotent. Well, why is that? Well, that's because it just contains its nilpotent part. But it's nilpotent for all elements of the Lie algebra. But if all elements of the Lie algebra are nilpotent, then the Lie algebra itself is nilpotent. Okay, But now if the Lie algebra itself is nilpotent, that means that the Lie algebra is solvable. So just recall we proved that earlier, that nilpotent implies solvable. Okay, but then if L is solvable, that means that the radical of L is equal to L. Remember that the radical is the largest solvable ideal of a Lie algebra. But if the Lie algebra is solvable, then its largest solvable ideal is, well, the Lie algebra itself. But that's non-zero. But then recall that if the radical is non-zero, then that means that L is not semi-simple. And that's because, well, what's the definition of semi-simple? Well, it means that you have a zero radical. You have no solvable ideals. So, well, that gives us our contradiction. Okay, well, what does that mean? Well, so that means that there exists some x in L such that s sub x is non-zero. So now let's just go ahead and call this s sub x simply s. And, well, let's observe the following. Let's observe that the span of this single vector s is a subalgebra of L. Furthermore, it is abelian. Well, it's abelian because it's one-dimensional. And furthermore, it has only semi-simple elements. And it has only semi-simple elements because, well, S itself was semi-simple by our original assumption up there. But notice that means that we at least have a one-dimensional Cartan subalgebra. So I guess to finish this thing off, we would just say, let's find the maximal subalgebra that contains S, and that would be an example of a Cartan subalgebra. Okay, so that means we've got a non-trivial Cartan subalgebra and we're done. Okay, so now let's move on to the next step. Now for our technical lemma, which will lead to the main result of the video. And that says if we have a Cartan subalgebra H and we take a little h inside of H so that the dimension of the centralizer of H is minimal, recall that that's going to be everything that commutes with little h. Then every s in H is in the center of the centralizer of H. So every s commutes with everything that commutes with H. So that's what's going on there with this like crazy condition here. And then that will imply that the centralizer of little h is contained in the centralizer of big H. But then the centralizer of big H is always contained in the centralizer of little h. That kind of goes without saying. That's something you could prove a long time ago, making those two things equal. So in other words, if you're able to choose this little h and h where this dimension is minimal, then, well, these two things are equal down here. That's like one of the things that we got out of this. Okay, so let's maybe prove this by contrapositive. So that means we're going to suppose that there exists an S in H such that S is not inside of the center of the centralizer of little h. Okay, so where is that going to bring us? Well, hopefully it's going to bring us to this dimension is not minimal because, well, that's what it would take to do this contrapositive type proof. Okay, so now we're going to do some technical linear algebra. So let's take a basis of the following subalgebra. So it's going to be CL little h intersected with CLS. Great. And maybe we're going to call this basis B sub 1. And it's going to be made of things like this. So I'll call them maybe Z1, comma Z2, all the way up to Zn. Okay, great. And then let's notice that the adjoint action of S is diagonalizable on CLH. Okay. That's because this adjoint action, well, is diagonalizable on the whole space. Okay, so now let's use this to extend B1 to a basis of, well, what? CL little h. So notice that CL little h will definitely be a subspace of the intersection of itself with something else. And well, we're not going to extend it just any old way. We're going to extend it with add S eigenvectors. And that's going to give us a new basis, but we're going to just zero in on the additional vectors. So as those additional vectors, I'll call x1, x2, up to x sub p. Okay, great. And now, well, now let's look that add h is diagonalizable on CLS. Well, add h is diagonalizable on the whole space, but it's definitely going to be diagonalizable on this subspace of the whole Lie algebra. And so now we're going to do the same kind of thing that we did up here. We'll extend B1 again to a basis, but this time instead of CLH, it'll be CLS, which also this intersection is going to be a subspace of that space, so that's how we can do that. And this time it's going to be with add H eigenvectors. Okay, so let's see. We've got these add H eigenvectors, and I'll call those y1, y2, all the way up to y sub q. Okay, so now let's see what we can do with all of that stuff. Okay, so we're going to take all these vectors that we had on the last board and push them all together into this set that I'll call B2. And well, now let's quickly observe that add S of Zi and add H of Zi are both 0. And that's because these Z's formed a basis of the intersection of the sets that commuted with S and H. So of course, if you apply the adjoint action of each of those, you will get 0. But then x1 through xp, those were going to be eigenvectors of add S. So that means that when you do add S xi, you'll get lambda I xi. And that lambda I is non-zero. And that's, well, immediately true because add H of xi was equal to 0, just because of this being an extension to the subspace CLH. So they have to be in the centralizer of H, meaning they commute with H. Now we know that those lambdas are non-zero because if they would be 0, then xi would be in the centralizer or the intersection of the two centralizers, which we know that it's not because we already had a basis for that. Okay, and then we've got a similar structure over here with the y's, where those had an eigenvalue mu I, which was not equal to 0. Okay, and now we're going to take this setup we have and prove the following claim, and that is that B sub 2 is in fact a basis of this sum of subspaces. So I'll call this CLH plus CLS. Okay, great. Now, how is this claim going to be proven? So let's notice that the spanning is pretty much done. And the spanning is done because we can get something inside of CLH by using Z's and X's. Remember, the X's extended the Z's to be a basis of CLH. So if it's a basis, then that spans. And then in order to get something inside of CLS, you'll use the Z's and the Y's for kind of the same reason. So if you can get something inside of CLH and something inside of CLS, then you can get something inside of both of them. So since the spanning is clear, all that we really need to prove is the linear independence. Okay, so let's see how that might go. So I'm going to take an arbitrary linear combination of these vectors that is, set equal to 0, and hopefully each of the coefficients will be easily shown to be equal to 0. We'll take a1, z1, added all the way up to an, zn, plus b1, x1, added all the way up to bp, xp, plus c1, y1, added all the way up to c, q, yq is equal to 0. And then, well, let's maybe give this thing a name just for the ease of use. Maybe we'll call this whole thing little w. Okay, great. But now let's notice that 0 is the same thing as add s of w. That's because, well, w is 0. But then s commutes with what? Well, s commutes with all of the z's, and s also commutes with all of the y's by our construction. So that's simply going to leave us all of the b's tied with their add s eigenvalue. In other words, we're going to have something like this: b1 lambda 1 x1 added all the way up to bp lambda p xp. But then that's equal to 0. But then that's a partial linear combination of a basis of CLH. Remember that the z's and the x's make a basis of CLH. So since that's a basis, well, it's linearly independent. So we've got a sum of things from a basis are linearly independent. Well, what that means is that each of the coefficients is linearly independent. But observe that none of the lambdas are linearly independent, or are equal to 0, I should say, by our assumption, meaning that all of the b's are equal to 0. So in other words, bi is equal to 0 for all, necessary I. And now, well, we're going to do the same thing with an add h. Notice that 0 is equal to add h of w, but then that's going to pull out the y's. That's because add h of the z's is 0 by our assumption that the z's were a basis of things that were in the centralizer. And then same thing, add h of the x's will be 0, but that add h of the y's will not be 0. This will be equal to what? So it's going to be like c1 mu1 y1 added all the way up to cq mu q yq. But again, we can do the same kind of thing that we did before. This is a linear combination of elements of a basis. Remember, the y's and the z's were a basis for, what was it, CLS. Okay, so that means that every coefficient in this linear combination has to be equal to 0, but none of the mu's are equal to 0, meaning that all of the c's are equal to 0. So that means that ci is 0 for all I. But now what we can do is plug the fact that all of the b's and all of the c's are equal to 0 up into our original equation, telling us that a1 z1 added all the way up to an zn is equal to 0. But then all of the z's are a basis of CLH intersected with CLS. But we've got a linear combination of basis elements being equal to 0, meaning all the coefficients are equal to 0 again. So that means that AI is equal to 0 for all I. But that means that all coefficients of our original linear combination were equal to 0, proving linear independence of our set. That, together with the clear spanning argument, means that yes, we have a basis of this subspace CLH plus CLS. So let's see where we go from there. Okay, so next up we're going to make the following observation, and that is that H and S commute. And that's because they come from an abelian subspace. Recall that they're both elements of big H, which is abelian, just by the definition down here of a Cartan subalgebra. Okay, but H and S commuting means that add H and add S also commute. But commuting linear transformations are simultaneously diagonalizable. So that's nice. So let's get that written down. Okay, so they're simultaneously diagonalizable. So now what are we going to do? Well, we're going to extend to a basis of the whole space. So let's do that. So let's extend B2 to a basis of all of L with the eigenvectors of add H and add S. I guess like the missing eigenvectors, because the basis B2 already contains, you know, a good portion of eigenvectors of both of them. But since they're simultaneously diagonalizable, then we have a basis of the whole space of eigenvectors. And so that's what we're doing here. So let's call these eigenvectors maybe W1 through WR. Okay, great. And so, well, what does our basis look like? So our B now looks like Z1 up to Zn, and then we have X1 up to XP, we have Y1 up to YQ, and we have W1 up to WR. Okay, great. So there's a basis of the whole space. And then, well, we also know that add H on WI is going to be equal to theta I times Wi. That's the eigenvalue-eigenvector relationship. Add S on Wi is going to be equal to, let's maybe use sigma I times Wi. That's again the eigenvector-eigenvalue relationship. Furthermore, we know that theta I and sigma I are non-zero. Because, well, if one of them was 0, they would be one of the xi's or yi's. If they were both 0, then the wi would have been one of the original zi's. So we know that neither of them are 0 here. So I think what's interesting here is we're decomposing this basis into 4 pieces based off of H and S. A piece that commutes with both H and S, a piece that commutes with exactly one of H and S, and a piece that commutes with neither H and S, this piece that is the W's. And then from here, what we'll do is form this like number, and this number will be called alpha. And so it's going to come from the following set. So, or sorry, it's going to be outside of the following set. So 0 minus sigma 1 over theta 1, all the way up to minus sigma r over theta r. So alpha can be any of these numbers. Then, well, we're going to have the following claim, which we'll finish up on a clean board, but I want to get it written down while we have all of the parts right here. And that is that CL of S plus lambda H, so that new vector that's constructed out of this number, which I guess we're calling alpha, is equal to CLH intersected with CLS. Okay, great. So let's see how that goes. Now let's look at this claim based off of the construction that we've had so far. So now this is going to follow from some observations, some little calculations. So let's look at the adjoint action of S plus alpha H on one of these vectors xi. So notice that that's going to be add S of xi plus alpha times add H of xi, just based off of how the adjoint action works. But then let's recall that this part goes to 0, leaving us with lambda I xi, where lambda I is not 0. So that means the xi's do not commute with this x plus alpha h. In other words, xi is not inside of the centralizer of xs plus alpha h. Okay, great. And then I'll just say similarly, so this is via calculations almost exactly like what we have right here. I maybe leave that as a homework exercise. You'll see why alpha was chosen the way that it is. And what we'll see is that yi and wi are also not inside of CLS plus alpha h, whereas our zi were inside of this centralizer. Okay, great. But now let's observe that the zi's formed a basis for this intersection. So since the zi's formed a basis for this intersection, that tells us that immediately we have CLH intersected with CLS is contained inside of CLS plus alpha H. But then the CLS plus alpha H did not contain any of the other vectors that extended our original basis to a basis of the whole space. So that means it can't contain anything outside of this intersection. But yeah, that means that we definitely have an equality here. But then let's go back to one of our original assumptions down this path. And that was S was not inside of the center of the centralizer of CLH. But that tells us that the dimension of the CL of S plus alpha H, which is equal to the dimension of CL of H intersected with CL of S, is strictly less than the dimension of CL of H. That's because, well, this element S is inside of here, but it's not inside of here. So that means when we make the intersection, we get something smaller. But observe what we have here. We've constructed this element S plus alpha H that produces a smaller dimensional centralizer. But recall that H was chosen so that the dimension of the centralizer was minimal. And so that forms our contradiction, or the end of our contrapositive proof, meaning that yes, this S had to be in the center. Okay, so now let's see how this takes us to these remaining statements. So now to finish this thing off, we're going to notice that if every S in H commutes with everything from the center of the centralizer of little h, what that tells us is that for all S in H, we have the centralizer of little h is contained inside of the centralizer of S. Okay, but then now we can just intersect using this for all statement to get that the centralizer of little h is contained inside of the intersection over all S in H of the centralizer of little s. But this exactly gives us the centralizer of the whole Cartan subalgebra. But then that gives us this inclusion right here. And then we started this whole thing off by saying why that immediately gives us this equality. So that finishes this proof. Now let's move on to our main result. So our previous result essentially said that there existed a little h so that the centralizer of little h is the same thing as the centralizer of big H. And well, we know that just by taking the little h that makes that minimality of the dimension of the centralizer. But now what we'll prove is that not only is the centralizer of little h the centralizer of big H, but it's in fact equal to the entire Cartan subalgebra. Okay, so let's get to it. So let's recall that one of the things about a Cartan subalgebra is that it's abelian. But since it's abelian, everything inside of the Cartan subalgebra commutes with everything inside of the Cartan subalgebra. So that means that the Cartan subalgebra is a subalgebra of CLH, the subalgebra of everything that it commutes with. Okay, so, but that was equal to CL little h by, well, our assumption here. That's how we chose this little h. And like I said before, the lemma before helped us know that we were able to choose such an h. Okay, so now where do we go from here? So now let's suppose that we've got an x inside of CL little h. And well, what do we want? Well, we probably want to get that x inside of h. So let's see how we can do that. So this is going to have a decomposition based off our previous result. X equals S plus N, where S is semisimple and N is nilpotent, like this over here, but I won't write it down. And then notice that what do we know? So we know the bracket of X with little h is equal to 0. That's by our assumption of X being in the centralizer. And then by the end of this result right here, we know that the bracket of S with H and the bracket of N with H are also equal to 0. So again, that's by this tagged on part of our previous result. But then, well, what does it mean for those brackets to be 0? That means that S and N are also inside of the centralizer of little h. And now let's quickly point out where we're trying to go. So what we'd like to show here is that S is in H. Well, remember that S is the semi-simple part and capital H, the Cartan subalgebra, is made up of only semi-simple elements. But like I said, S is the semi-simple part of X. And then, well, if we can also show that the nilpotent part is 0, then that'll show that this X is inside of H as needed. Okay, well, let's maybe do this first part first. So in other words, we'll prove that this semi-simple part of X is inside of the Cartan subalgebra. Okay, so how might this little sub-proof go? Well, let's note that S is inside of CLH, which is CL big H by our original sort of assumptions and calculations. That tells us that the bracket of Y with S is equal to 0 for all Y inside of H. That's what it means to be inside of this space right here. But then we immediately get that S is inside of H because notice that H plus CS, in other words, the vector subspace that's H along with the vector S, well, this is an abelian subalgebra with only semi-simple elements. So we know it's abelian because H is abelian, and then S commutes with everything inside of H, so the whole thing is abelian. We know it has semi-simple elements because H has only semi-simple elements, and S itself is semi-simple. But then we also know the following, that the dimension of H is less than or equal to the dimension of H plus CS, because it has, well, perhaps one new basis vector S. But then by the maximality, we know that the dimension of H is bigger than or equal to the dimension of H plus CS. But then we've sandwiched these things together with their dimensions, so their dimensions have to be equal, meaning that H is equal to H plus CS, but that can only hold if S is inside of H, as needed for this claim. So let's maybe put a box around this and we'll put a check mark next to it because we finished that and we're ready to show that N is 0. Okay, so now we're going to show that this N is equal to 0, and we're going to do this in 2 steps. We're going to start by showing that the subalgebra CLH is nilpotent. Okay, so how can we do that? Well, let's take some arbitrary element, I'll call it Y, inside of this CLH. So, and then let's write Y as S sub Y plus N sub Y. It's semi-simple and nilpotent parts. And then we're going to consider the adjoint map of Y from CLH to CLH. So as a linear transformation. And let's observe that this adjoint map decomposes as the adjoint map of SY plus the adjoint map of NY. But what do we know? But we know that SY is inside of H by, our previous result applied to this Y vector instead of the X vector. So by this result up here that we have with this check mark. But what does that tell us? That tells us the adjoint action of Y is the same thing as the adjoint action of the nilpotent N sub Y. Well, that's because this sy is inside of h, but then this CL little h is the same thing as CL big H, so everything commutes with this sy by their construction. But then putting this all together, we have for all y inside of CLH, the adjoint action of y from CLH back to itself is nilpotent as a linear transformation. But then if this is nilpotent as a linear transformation for every element, well then that means by Engel's theorem, CLH itself is nilpotent. But look, that's the first thing that we wanted to prove, the first of our two steps. So now let's move on to the second step. Okay, so the second step will be to prove that every element of CLH is semisimple. But look, that's gonna finish this proof that n is equal to 0. Okay, so let's get to it. We're going to use this fact right here. So CLH nilpotent, that'll be the first thing that we start with, our first step of this little claim. But that means that CLH is solvable. Remember, we've used this result already today. But then also, by Lee's theorem, there exists a basis of the whole space L such that add x is upper triangular. Recall that semisimple was like an abstraction of upper triangular, but then Lee's theorem tied those two together by a choice of a basis that made the whole thing upper triangular. So also, we know that add x is equal to add n on this CLH, so the restricted linear transformation. But then if x collapses to its nilpotent part, that means that add x is strictly upper triangular. So remember, nilpotent means strictly upper triangular. But then let's take some sort of y inside of CLH and then do the killing form of n with y, which let's recall that that's the trace of the adjoint action of n with the adjoint action of y. But then given the fact that the adjoint action of n is the same thing as the adjoint action of x, which is upper triangular, strictly upper triangular, we know that this trace will be equal to 0. But then we also know from a previous result that if we take kappa and we restrict it to CLH, it is non-degenerate. But then we essentially showed above that for all y, kappa of n with y is equal to 0. But then this non-degeneracy means that the only way for this to be possible is for that n to be equal to 0. Okay, but that means that we've sorted it. This n was equal to 0, meaning that x is equal to s, but then we showed s was in h, so that means x is inside of h, completing this proof. And that's a good place.